Hello guys, and thank you for watching this lecture as part of a broader series on probability and statistics. First, let's see where we are right now. We are learning a series of lectures on probability and statistics. We already learned that the probability is the science of predicting the likelihood of events based on known rules or models. Probability starts with a big picture, a theoretical framework, and drills down to specific outcomes. On the other side, statistics work in reverse. Statistics begin with specific data points, those of observation from the real world, and it uses them to build a broader understanding of patterns or trends. In essence, probability moves from the whole to the parts, while statistics moves from the parts to the whole. Now, the statistic itself has two main branches, descriptive statistics and inferential statistics. Descriptive statistics is about summarizing and organizing data. Think of mean, percentage, or charts that paint a clear picture of what is happening. On the other side, inferential statistics takes things a step further. Inferential statistics uses sample data to make educated guesses about a large population. When it comes to inferential statistics, we often rely on several approaches: point estimation, confidence interval, as well as hypothesis test. A point estimate, as we studied in the previous lecture, gives us a single, and that is the best guess for a population parameter, like estimating the average height of a group based on a sample. But point estimates do not tell us the whole story because they lack a measure of uncertainty. That brings us to confidence interval, which we will focus on today. A confidence interval provides a range of values based on sample data that likely contains the true population parameter, along with a confidence interval that quantifies our certainty. It's like saying we are 95% confident that the average height of this population falls between 170 centimeters to 180 centimeters. So let's explore confidence intervals in detail and see how they empower us to make informed decisions in an uncertain world. In this lecture and the next lecture, we will study inference procedures designed to investigate the population mean, or mu. We will study two inference procedures including confidence interval construction in this lecture and hypothesis testing in the next lecture. Today, we will walk through 5 key areas: the t-distribution and why this t-distribution is essential when the population standard deviation is unknown. Then we will study how to construct confidence intervals for population means. Next, we will see the impact of sample size on accuracy and precision of these intervals. Later, we will study one-sided confidence intervals which are useful in specific testing scenarios. And finally, we will see how to use z-intervals when the population standard deviation is known. So let's get started. Let's begin with the t-distribution because we need it later. The t-distribution models the standard distance between the sample mean and the true population mean when we do not know the population standard deviation. So the population standard deviation is unknown to us. The t-distribution resembles the normal distribution because it is smooth, symmetric, and also it is centered at zero. But there are some differences. The t-distribution is slightly wider to account for additional uncertainty due to estimating the standard deviation from the sample. The normal distribution assumes that the population standard deviation is known, while the t-distribution does not make this assumption. Importantly, the shape of t-distribution depends on the degree of freedom. What is degree of freedom? Degree of freedom is sample size minus 1. So as the sample size increases, the t-distribution converts to the standard normal distribution. The t-distribution is most useful for a small size sample when the population variance and standard deviation is unknown to us. So in this graph, we can see one is normal distribution with 3 different cases of t-distribution. So as you can see here, this green color is the normal distribution, and this orange, blue, and purple, these are the t-distribution. So this orange is for degree of freedom 10, the blue is for degree of freedom 2, and the orange is 1. You can see here that t-distribution has a fat head and tail, right? So the distance between this here and here is more than normal distribution. It means the distance between 2 and x-axis is more than the normal distribution. So what is confidence interval? Confidence in statistics is another way to describe probability. A confidence interval is the mean of what we have estimated plus and minus the variation in that estimation. So a confidence interval for an unknown parameter is an interval that contains a set of plausible values of the parameter. So here we are talking about plausible. This is not the same as possible. Plausible refers to values within the interval that are likely to include the true population parameter with the specified confidence interval. For example, 90%, 95%, or 99%. On the other side, possible includes any value that could theoretically be the true parameter, even those outside the interval with lower likelihood. So these two words are different. And in here, we are working with plausible values. So then we have confidence level. The confidence level represents the long-run proportion of such intervals that will contain the true value of the parameter across repeated sampling. So confidence interval is always associated with a confidence level that is 1 minus alpha. And this confidence level measures the probability that the confidence interval actually contains the unknown parameter value. We have some known confidence levels like 90%, 95%, and 99%. 90% corresponds to alpha is equal to 0.1. It means that we are confident that 90 out of 100 times the estimate will fall between the upper and lower values specified by the confidence interval that you can see here. Then we have 95%, and in here alpha is equal to 0.05, and in here we have 99% that is correspond to alpha 0.01. And the confidence level quantifies the experimenter's degree of certainty that the population parameter like mu is contained within the calculated confidence interval. When we infer about the population mean using some small samples, for example, less than 30, and also we don't know the population standard deviation, then we use what is called as T procedure. This is only valid when our data come from a population that is approximately normally distributed. In such cases, we use sample standard deviation and the T distribution to compute the confidence interval. So, for inference on population mean, normally T procedure or T intervals are used. It is applicable on the observation from a normal distribution, as I said, and we generally use it for sample less than or equal to 30. Even if it is more than 30, but a standard deviation is unknown, we can go for the t-test. T-intervals provide a sensible analysis unless the data observation are clearly not normally distributed. So we have two-sided t-interval and one-sided interval. Now we want to study two-sided interval. Two-sided interval is the most commonly used confidence interval for the population mean based on a sample of n continuous data observation with a sample mean and sample standard deviation. This two-sided t-interval is also known as variance unknown confidence interval. This one says to us that the mu, the true parameter of the population, lies in this interval, right? X bar minus, this is the critical point, and x minus this value, I'm going to explain later, and x bar plus this value. So it says the mu is in this interval. In here, mu is our population mean. Then x bar is our sample mean, right? So x bar minus this part, x bar plus this part. So as you can see here, x bar is here, x bar this plus this value, x bar minus this value, right? So T alpha divided by 2 and minus 1, this is known as critical point. This n is the sample size. This S is a sample standard deviation. And this n is again sample size. So we have one new terminology here, critical point. A critical point is the value from a statistical distribution, like for example, z-score or t-score. We use this critical point to determine the margin of error that corresponds to the desired confidence level. So in this figure, we show a two-sided t-interval. The interval is centered as the best guess, or we can say mu bar or x bar, that is our sample mean, right? And then it expands on either side by an amount equal to the critical point. You can see here, critical point, alpha by 2 n minus 1 multiplied by the standard deviation divided by root square of n. So x bar plus this value, x bar this, and we say that mu with, for example, 95% or 99%, the mu falls in this interval, right? Because we are going to predict a mu, right? And this two-sided interval say by the probability of, for example, 95%, our predicted mean will fall in this interval. In the point estimation, we say, for example, the true population mean is 95, right? It means 1 point, we say, but in here we are talking about interval. For example, instead of saying 95, we say from 93 to 97, right? It means 95 plus 2, 95 minus 2. So this value s divided by n is known as a standard error, right? Standard error and standard deviation are not the same. A standard deviation measures the variability of individual data points around the mean. On the other side, standard error quantifies the precision of the sample mean as an estimate of the population mean. So we can write this one. So let me clean this one. We can write this one as, again, mu is in these two values, right? These two values. Mu hat minus critical point, this one, multiply standard error of mu hat, this one, right? And the same here, mu hat plus critical point multiply standard error, right? SE of mu. The standard error is the standard deviation of the sampling distribution of a statistic, like the sample mean. So the question is, what is the length of two-sided interval? The length of two-sided interval is L, 2 multiply the critical point, a standard error, right? So this is the critical point and this is the standard error. A lower standard error implies a narrower and more precise confidence interval. So here in this image, you can see the difference between the length of, you can see two confidence level, 1 minus alpha 1, 1 minus alpha 2. And you can see here that a lower standard error, it means a narrower but a more precise confidence level. Also, as the confidence level increases, for example, from 90% to 99%, the critical value increases and the interval becomes wider to ensure a higher level of certainty. The length of two-sided t-interval is proportional to the standard error of mu hat, this one. As a standard error of mu hat increases, so that mu hat becomes equal to x bar, so that mu bar equals to x bar becomes a more accurate estimate of mu. It means a more accurate estimate of mu allows the experimenter to eliminate more values of mu from contention. The length of confidence interval also depends on the confidence level that we have. As the confidence level increases, the length of the interval also increases, as you can see here. It is also depends on the critical point that we have defined here. We know that root square of n x bar minus mu divided by s follows a tn minus 1. This equation indicates that the standard sample mean adjusted by sample standard deviation s and the sample size of n follows a t distribution with n minus 1 degree of freedom. We use this equation for confidence interval or hypothesis testing when the standard deviation is unknown to us. From this equation, we can see that the standardized root square of n x bar minus mu divided by s, this measures how far the sample mean x bar is from the population mean mu in standard error units. This follows a t distribution with n minus 1 degree of freedom. And so the definition of the critical point of the distribution ensures that the probability of this root square of n x bar minus mu s between minus critical point and plus critical point is equal to 1 minus alpha. This equation indicates that the standardized statistic that lies between the critical values between minus and plus critical values is equal to 1 minus alpha. This defines the confidence interval. It means there is 1 minus alpha percent chance that the true population mean lies within the interval defined by these bounds. So by rearranging this inequality, we can solve that mu is between x bar minus this value and x bar plus this value, right? It means mu falls between x bar minus this value and plus this value. So this interval estimates where the true population mean lies between 1 minus alpha percent confidence. So if I want to state this equation in words, there is a probability of, so we say because probability of these values is equal to 1 minus alpha. So I can say that there is a probability of 1 minus alpha that the random confidence interval limit takes values that straddle the fixed value of mu, right? It means the probability that mu falls between x bar plus this value and x bar minus this value is equal to 1 minus alpha. So let's see one example to better understand what we learned so far. Consider this data set. So we have a data set here, and these are 60 measurements of metal cylinder. So we have like n is equal to 60, then the median is 50, the maximum value is 50.36, the mean sum of all divided by 60 is 49.999, upper quartile is 50.07, the minimum value is 49.74, and the standard deviation, that is the each value minus mean square divided by n minus 1, and that root square of the variance is equal to 0.134, and the lower quartile is 49.91. So the population may be the set of all cylinders produced by that company. So now we want to find the critical points for different confidence level with 90%, 95%, and 99%. We already know that n is equal to 60, but based on the equation, we say n minus 1, right? So you can see here T alpha divided by 2 n minus 1, right? So that's why we have 59 here, 60 minus 1, right? Then this 0.01 for 90%, we already found here for 90%, this is 0.1, right? And this one divided by 2. So these things divided by 2 is equal to 0.05, 0.025, and 0.005, and 59. So now the question is how to find this value. Do you remember already we have something called a z-table? We have also something called as t-table, right? The t-table is the upper critical value for t distribution. Degree of freedom is 59, so 59, then we go for the 0.05, then we go for 0.025 and 0.005, right? So for this one, 0.05 and 59, 161, then 2001, 22001, and 26662, right? So these are the values. If we can find the critical points, right? So we found that the critical point for confidence level of 90% with the degree of freedom 59 is this one, and the same for 95 and for 99. Here we can find the confidence interval for different confidence levels like 90%, 95%, and 99%. We have already the equation that mu falls between x bar minus x bar plus, right? Then in here, critical value T alpha divided by 2 and n minus 1, and in here, s divided by root square of n. Then again here, x bar plus T alpha divided by 2 n minus 1 root square of s divided by n. So we already find these values here. Just substitute here. We have x bar is all 49.99. Then for the first one, what we found here, 1.671. So 1.671 is here, 2 and here. So we already found these values, right? Just you put it here. Then multiply S, standard deviation that we found here, 134. So 134, 134, 134, all 134, and root square of n, the sample size, right? Then we will find, so if you solve this, you will come up with this value and this value. Then we can say 90% confidence interval is 49.97 and 50.028. It means by the probability of 90%, by the chance of 90%, by confidence of 90%, the mean falls between these values. In here, with 95% it goes to this interval, with 99% it goes to this interval. You can see here, as the probability increases, this becomes wider. So we found that with 90%, 95%, and 99%, these are just figure representation of these values. So you can see here, it becomes a little bit. So this one is narrower, right? It be a little wider because the probability increases. So with our 99% certainty, the average cylinder diameter lies between 49.93 to this one, right? So it is important to remember that this confidence interval is for the mean cylinder diameter and not for the actual diameter of a randomly selected cylinder. All right, now let's try the same example in Python. To do that, we need to import numpy as np. Then we need to import scipy.stats as stats. And also for plotting, we need to import matplotlib.pyplot as plt. All right, now we have to bring our data set. Data is equal to, I will copy paste our data here. All right, this is our data set. It means sample. Now we want to calculate whatever we had. So first we want to print the sample size, right? So sample underscore size is equal to length of our data, right? And then we can print it, print if then sample size is equal to, then here sample underscore size. So it is 60. Next, we want to print the median, right? So median is equal to np.median of our data, right? And then in the same way, we can print if the median is this one with 2 decimal places. Next, we want to go for max, right? So print if max is equal to np max of data, which is 50.36. Then we will print the mean of our data, which is equal to np.mean of our data, 49.74. Next, we're going to find the mean value, right? Print if mean is equal to mean of our data, which is 50, but it was not 50, right? So let's go for 4 decimal points, 49.99, right? Then after mean, we go for percentiles. So print f, then upper quartile is equal to percentile of data, NP percentile of data, and 75, which is 50.07. In the same way, we can go for lower quartile. The lower quartile will be the same, but in this case, we will have here 25, and we will change this one to lower. So lower is 49.91. Then we can print the variance. So print f, then sample variance is equal to np dot var of data, and the degree of freedom is equal to 1, right? And then we can print the standard deviation. So print f standard deviation, which is equal to np dot std of data, and degree of freedom is equal to 1. Next, I'm going to print the standard error. So print f, then standard error is equal to np dot some standard deviation of data, and degree of freedom is equal to 1 divided by np dot sqrt of what? Sample size. Sample size. I want to calculate and print critical points and confidence interval for confidence of 90%, 95%, and 99%, right? So we define confidence levels is equal to 0.9, 0.95, and 0.99, right? So now I'm gonna calculate the confidence levels, right? So for I in confidence level that we have defined here. So in here, alpha is equal to 1 minus this I. It means 0.9, 0.95, and 0.99, right? Then the degree of freedom is simply sample size minus 1. So degree of freedom is equal to sample size minus 1, right? Then in here, I'm gonna calculate the critical point for two-sided confidence interval, right? So critical underscore point is equal to stats.t.ppf. I call this function from t distribution in stat that we have imported already, right? And in here, we will pass 1 minus alpha divided by 2 and degree of freedom. So this PPF stands for percent point function, that is inverse cumulative distribution function. We have imported this one from scipy.stats, and this module returns the critical value, like t-score, for the t distribution for a given significance level, that is 1 minus alpha divided by 2, and based on the degree of freedom. Then in here, I can print, right? Print if confidence level of I multiply 100% of critical point is what? Critical underscore point, and we show it with 3 decimal places, right? So based on the table that we had, for 90% it is 1.671, for 95% is 2.001, and for 99% is 2.662, right? So this is correct. Now it's time to calculate the confidence interval. First of all, we need to find the margin of error. So margin of error is critical point multiply the standard error, right? And then here we need to find out the lower bound and upper bound, right? So I underscore lower bound is equal to np dot mean of our data minus margin of error, and I upper is equal to mean of data plus margin of error. Then confidence interval, I multiply 100%, I lower up to, for example, 4, and I upper 4, right? So you can see here, let's add this one here, right? So this is the confidence level for 90%. Critical value is this one, right? And confidence interval is 49.97 to 50.27. Then here is 2001 for 95% and 49.964 up to 50. And this one is for 99%, right? This is exactly based on what we calculated in the PowerPoint. And also here, we can add the confidence interval length, right? So confidence underscore length is equal to I upper minus I lower, then we can print it, confidence length up to 4, right? So this is the confidence length for each one, right? It means the upper one minus the lower one. Now, I want to try some plotting. So first of all, I'm going for plot this data in histogram. So plt.figure, and then fig size is equal to 8 and 6, then plot histogram data, and bins is equal to edge color black, and alpha here, alpha point at transparency. Then plt.title histogram of data, and X label, Y label, and grid as well, right? So this is the histogram of our data. So if I change this one to 10, you can see this is the histogram of our data. We can also go for box plot. So just plt.box plot, and we will pass our data, and vertical is equal to false, right? So this is our box plot of our data. So you can see here, this is our box plot. And finally, the important thing here, I want to show the confidence interval on the plot, right? So for I in confidence levels, then alpha is equal to 1 minus I, the degree of freedom is sample size minus 1, then critical point is stats ppf 1 minus alpha 2, and degree of freedom, margin of error, is equal to critical points multiply the standard error that we already calculated here. And this is for margin of error. We need I lower, I upper, and then we can plot it, right? So plt dot error bar, and then here we will pass I, and then sample mean of data, then y error is equal to I upper minus mean of data, and then here fmt is equal to O, and label it as upper is equal to f I multiply 100% I, right? Some error here. This should be here, and FMT, and this one. That's correct. So in this line of code, we plotted one error bar, that is a matplotlib function, plots data points with error bars to indicate variability or uncertainty. This YERR, this Y error, indicates the length of the error bar about the sample mean. So let me add some more information to it. Then here, plt.ax line, then np dot mean of our data, I want to show the mean. Color is equal to, for example, gray, and line style is like dashes, and label is equal to sample mean, right? Error. PLTAXH line, horizontal line. All right, so this is our sample mean, a little bit less than 50. Then I can add here, like, for example, plt.title, legend, and also plt.grid, right? So this plot is very beautiful plot, and it gives us some information. So you can see here, this is the sample mean, a little bit less than 50. Then for the 90%, right, for 90% confidence, we can see here, this V is from, so it should be confidence interval, all right. You can see here, this is for 90%. So it was from 49.97 up to here. This is for 95%, which was 49.64 up to 50.03. And this is for the 99% from 49.95 to here, that is 50.42, right? This graph in a beautiful way shows us what we have learned in this lecture. In some slide before, we saw that the length of two-sided t-interval is L, critical point, standard deviation divided by root square of L. For a fixed critical point, a confidence interval length like L is inversely proportional to the square root of the sample size of N. So we here notice that this dependence of the critical points on the sample size also serves to produce smaller confidence intervals with large sample size. If a confidence interval with a length no larger than L0, we want a confidence interval with the maximum length of L0, then we can find the sample size. So the sample size is N greater than or equal to 4 multiply critical point S standard deviation of sample L that we receive in power of 2. So suppose that an experimenter wishes to construct a 95% confidence interval with a length of no larger than 2 millimeter for the mean thickness of a plastic sheet produced by a particular process. Previous experience with the process enables the experimenter to be certain that the standard deviation of the sheet thickness cannot be larger than 4 millimeter, and a larger enough sample size is expected so that the critical point, this one, will be less than 2.1. So in summary, for the mean thickness of a plastic sheet, an experimenter wishes to construct a 95% confidence interval with a length no larger than 2 millimeter. So the known fact is that the standard deviation here, the STD, is less than or equal to 4 based on here, right? And we have assumption here that TO025 and N-1 is less than 2.1. So we can write it this way: T0025 and N-1 is less than or equal to 2.1. So this is for a large enough sample size. Then to multiply critical point standard deviation root square of n is less than. So we found that the critical point is 2.1. The standard deviation is 4 divided by root square of n is less than L0. And we have already L0 here. This L0 should be 2, right? Then based on this formula that we have here, we can bring this L0 here. This is L0. And then you can find out this value. So we found that n is equal to 70.56, but n must be an integer. So we round it up to 71, and we conclude that the minimum sample size required is 71. In most of the cases, we need to take many samples. For a sample size like N1 and a sample standard deviation like S, the length of the confidence interval is equal to critical point standard deviation divided by root square of N1. In order to reduce the confidence interval length from, for example, L0 less than S, the size of the additional sample required is n minus n1, where n greater than 4 critical point standard deviation and sample size. In a couple slides before, we had an example of metal cylinder production. The sample size is 60, and we found that 99% confidence interval between these intervals. The confidence length is critical point standard deviation, and this one, so 2 multiplied 2.6 divided by root square of 60 is 0.092. The question is here, how much additional sampling is required in order to provide increased precision of a confidence interval with a length of 0.08 millimeter at the same confidence level? The answer is a total sample size required is n greater than 4 based on the equation that we had is equal to 79.53. We need an additional sample of at least, so if you consider this one as 80 and we already have 60, so we need 20 more sampling. It means about 20 more samples are needed to reach this increased precision. Now let's see what is a one-sided t-interval. There are times we are only interested in a bound in one direction. So one-sided confidence interval with confidence level of 1 minus alpha for a population mean with mu on the sample of n continuous data observation with the sample mean of x bar and the sample standard deviation of s, then we say the mu falls in this way we have minus infinity. In here we have plus infinity, right? In there we say x minus this value, but instead of that value we have minus infinity. And instead of x bar plus that value we say plus infinity. That is called as one-sided, right? This provides an upper bound of the population mean, and this one provides a lower bound on the population mean. So we already learned this one. This measures the difference between the sample mean x bar and the population mean like mu in standard error units. It means with a sample standard deviation of s. And this follows a t-distribution with n minus 1 degree of freedom. Then in here, we want to find the probability of this value, right? The probability that the standardized statistic is greater than the critical value for the t-distribution with n minus 1 degree of freedom at the significance level of alpha is equal to 1 minus alpha. So this defines the confidence level for upper bound. Right? Then in here, just we rearrange the inequality of here, and we found that the probability of population mean less than x bar plus t alpha minus 1 critical point standard deviation root square of n is equal to 1 minus alpha percent confidence. And we know already that this s divided by root square of n is a standard error, and this is the critical value. Then in here, we can write down in this way that mu falls between minus infinity to x bar plus critical point standard deviation divided by root square of n. Let's see another example here. Hospital workers who are routinely involved in administrating radioactive tracers to patients are subject to a radiation exposure emanating from the skin of the patient. In an experiment to assess the amount of this exposure, radiation levels were measured at the distance of 50 centimeters from n is equal to 28 patients who had been injected with a radioactive tracer, and a sample mean of 5.145 and sample standard deviation of 0.752 is obtained. With the critical point of this one, right, and 99% one-sided confidence interval. So we want to find this one. Mu falls between minus infinity to x bar, critical value, standard deviation, root square of sample size, right? So minus infinity, then x bar, this one, come here, plus critical point, this one, standard deviation, this one, and root square of 28, which is equal to minus infinity to 5.496. Now we come to z intervals. When the population standard deviation sigma is known and we use this sigma in confidence interval instead of the sample standard deviation s, then the standard normal critical point of z alpha divided by 2 is used instead of that one that we have already, t alpha divided by 2 and n minus 1. So we know sigma, we don't need to use sample standard deviation anymore, right? So in here we have sigma instead of s, and in here instead of t alpha divided by 2 and n minus 1 we use z alpha divided by 2. So once again, if an experimenter wishes to construct a confidence interval for a population mean of mu based on the sample size of n and the sample mean of x bar and using an assumed known value of population standard deviation sigma, then the appropriate confidence interval is mu between x bar minus these values and x bar plus these values. This is known as two-sided z interval or various known confidence interval. And the last topic here is one-sided z interval. So we can do the same thing for one-sided. So we know that standard deviation is known here. Then again, minus infinity, and this is the upper bound and lower bound, right? Minus infinity here plus infinity. X bar plus z alpha by 2 standard deviation divided by root square of n. This is the confidence interval, and this is known as one-sided z interval. Okay, that's all for today. Thank you very much for watching this video lecture. So to summarize, we use the t-distribution when sigma population standard deviation is unknown and also sample size is small, less than or equal to 30. We learned that confidence intervals offer a formal way to express uncertainty. We understood that larger sample size yield more precise intervals. And finally, we learned that one-sided intervals and z-intervals can be applied in some special context. So please feel free to ask me your questions by leaving a comment below this video lecture. Thank you and see you in the next lecture.